Okay, what we're going to look at now are isotopes. We've done basic atomic structure, protons, neutrons found in the nucleus, and electrons arranged in what we call shells, or energy levels around that. And we've done these shells, or energy levels, arranged with the first 2 electrons in the first shell, then the next 8, then the next 8, and so on. Isotopes have nothing to do with the electron configuration. We're only going to be looking at the nucleus. Doesn't matter if I'm not on it, but thank you. So here I've got 2 symbols, or what we call nuclides, for lithium. The number at the top, the bigger number, is what we call the mass number. The number at the bottom is the atomic number, so it's where I would find it on the periodic table. Okay. In a question we might be asked to compare and contrast these 2 atoms. Well, they both have the same atomic number and they both have the same symbol because they have the same atomic number. Atomic number gives us 2 things. It gives us the number of protons, so there'll be 3 protons there. Because there's no charge on these, they're just atoms, not ions, it also tells us the number of electrons. So if we were comparing and contrasting these, we would say that they've got the same atomic number, or they are the same atom, the same element, so therefore they have the same number of protons, and as they have no charge, they both have the same electrons, so the same electron configuration. Now the work we've done recently, we would also say if they have the same electron configuration, they must also have the same chemical reactivity. Right? They must have the same chemical reactions. So 2, 1 is their electron configuration. Therefore, they lose an electron to become lithium plus ions, and so they have the same chemical reactions. Alright, so they have the same chemical reactions because the atomic number is the same. We have to explicitly say which means they have the same number of protons, which means they have the same number of electrons, which means they have the same electron configuration. And that's why they have the same chemical reactivity. However, we can see that the mass number is different. And the mass number is important because it is the number of particles in the nucleus. We already know some of those particles, the protons. We've already been told there are 3 of them. So therefore, there must be a different number of neutrons, the other particles. So in lithium 7, and I'm going to ignore the 3 this time, in lithium 6, I can say that they have both got 3 protons. And now it's just a bit of a subtraction. 7 minus 3 equals 4. So it must have 4 neutrons. Whereas this one, 6 minus 3, has 3 neutrons. And it's sort of a bit of a so what. Well, there is something important about this. If there's more particles in the nucleus, then for a certain number of atoms, they have different masses. That's why it's called the mass number. This one is 1/6 heavier than this. So there is actually, they have a different mass. They also have a different mass for the same number of particles. They have a different mass. The reason this is important is just something we did in the last topic. Alright? EK equals half mv squared. Okay, m being mass. EK is linked to temperature. Okay, temperature is the average kinetic energy of all the particles in something. So at a given temperature, then the amount of kinetic energy would be the same for both of them. If the mass is different, so if the mass is higher for lithium 7, then its particles must be going slower. So if this was a gas, for example, and we need successful collisions to occur for a reaction to occur, then those particles are going slower, which means there'll be fewer collisions. This becomes important later when we do the collision theory as part of this topic. So this is going to have an impact later when we do collision theory. At the moment, though, just looking at atomic structure, we can say they have the same chemical reactions, but different masses because they have different numbers of neutrons in their nucleus, and showing how we calculate that. The far-reaching thing is that there will be a slight difference in how quickly they react, because they'll have different speeds. The particles will have different speeds because of their different masses. Right? So at a given temperature, that is, at any given temperature. That's basically isotopes in a nutshell. There's one more thing I want to go through. A lot of isotopes are what we call radioisotopes. They're a special subset. They are the ones which break down. They undergo a nuclear decomposition, is what we call it. So where the nucleus turns into something else. There are things like carbon-14, which you might have heard of as used for carbon dating, so finding out how old something is, and so on. And actually carbon-14 is quite a cool one, because carbon-14 somehow turns into nitrogen-14, and then the two nitrogens join together to make nitrogen gas, and it escapes. So it actually leaves it. When something's alive, then a certain percentage of its carbon is carbon-14, a certain percentage is carbon-13, and most of it is carbon-12. So when something dies, it's not eating plants and so on which make this carbon-14, incorporate this carbon-14. So it no longer replenishes it. So eventually the carbon-14 disappears as nitrogen gas. It just evaporates, basically. After this decomposition, it disappears. So the longer you've been dead, the less carbon-14 you've got in your body. And so we can use this idea to estimate how old something is. It doesn't have the accuracy of to the nearest year, but it is still pretty accurate when we're talking in thousands of years. And so it's often used as evidence for how old something is, say a fossil or something like that, by looking at the amount of carbon-14 left in it as a percentage, knowing that living things have a certain percentage and it just drops off over time. It just drops away. Actually, I've probably shown it at the wrong angle, so like that. Alright, and it's what we call radioactive decay, where something breaks down into something else, and it's used for working out how old things are. Alright, so isotopes are pretty cool, insofar as they do everything the same as each other, but actually the fact they're different masses might have an effect on their rate of reaction. But what's really cool about it is that some of them are what we call radioisotopes. They radioactively decay, and we can use this to find out how old things are that are millions of years old or thousands of years old. Right? And that's one of the key reasons why we learn about isotopes.